glad to be here to talk about digital biomarkers. So I know this is the last talk, but hopefully we can, that break got you guys energized again to get back into this. All right. So again, just wanted to start off by asking a question. How many of you guys know who this is? You can raise your hand, also type in the chat. All right, we got a couple of responses. Yay, yes, good job. All right, so Dr. Jane Goodall, right? She's known for her persistence and strong desire to study animals through natural observation, right? Despite no formal training. And she discovered human-like behaviors among chimpanzees in Tanzania in the 1960s. And so while we love the brave Jane Goodall, natural observation is hard. In some cases, it can be dangerous and does not scale and is burdensome. And more commonly, people use self-reports, right? Because it scales to study human behavior. However, these can also be biased and burdensome. So getting us into the digital biomarker and what we mean here by digital biomarkers, we define it as an objective, quantifiable, physiological and behavioral data that we can obtain from digital devices, wearables, implantables, digestibles. Now, Santosh also before spoke a little bit about stress and psychological factors that we can capture, but here we define digital biomarkers as mainly physiological and behavioral. And our objective would be to collect them to explain, influence, and or predict health-related outcomes. Common sources of data we know include the ubiquitous smartphone, right, which has so many wearable sensors and scales quite well. And more commonly now, the wearable space ranges from wearables on the wrist, to necklaces, earbuds, glasses, and even rings. Now, there are 5 steps that I like to sort of talk about here that's also delineated in this digital medicine paper to building and adopting biomarkers. The first relates to measurement, right? And here we're asking the question, are we building using the right device/system? The second step relates to verification. And so this here we ask the question, was the device/system built right? And then third, when it comes to validation, and here it's critical, is the biomarker generated meaningful, right? That we collected from these wearables or from these different devices. Now, all 3 of these steps need to pass for stakeholders to gain interest. And then there are other factors related to modularity and then regulation/implementation. Finally, this is an iterative process, right? And I hope in this talk to mainly focus on the first 3 steps and discuss some challenges along with important things to consider during each step when using or building wearables or working with, and a lot of you as clinicians would also be, these are important things to consider when working with clinicians, computer scientists. And hopefully you guys can put us back in check. I also mention a few insights when writing NIH applications. This is by no means a comprehensive sort of challenges, but also mainly my experience throughout developing digital biomarkers. All right, so Santosh spoke quite a bit about smoking, and so this is also a problem that is of interest in my lab. So let's go through, and so I want to start by going through some examples of applications that we target. And smoking is one we know that's deadly, 8 million deaths globally a year. We know that most adult smokers want to quit, but fewer than 1 in 10 actually succeed in quitting. And we want to detect smoking and antecedents like stress, but also detecting smoking can, it's not just the antecedent that matters, right? It's also the smoking event that could matter, right? And our ability to detect it, because smoking can help us trigger users to self-report contextual factors or for us to understand what triggers smoking during the pre-quit phase. During post-quit, we can start to detect lapses, right? So we can hope to begin to try things, right, to learn about what triggers might prevent a lapse from turning into a full-blown relapse. We may also want to see if we can detect smoking topography, or how a person smokes, number of puffs, puff volume, or chemical exposure, and also which has been shown to be useful in predicting abstinence post-treatment. All right, and so here I worked quite a bit with Santosh and Bonnie Spring, who you guys have heard from earlier today, in their MD2K project, Mobile Data to Knowledge project, on the Sense to Stop, right? And part of it was the Sense to Stop project. And here we were using wrist-worn devices to actually detect or capture the smoking gesture, right? More recently, we designed a thermal sensing necklace we're really excited about that can detect heat signatures to accurately detect smoking events and smoking topography in the real world. It's called SmokeMon. Some people think it's a play on Pokemon, but really SmokeMon is named after, we call this SmokeMon as a smoke monitoring device. And so here you can see, here we have a person smoking, and we can see a clear difference in the heat map when the smoker lights up the cigarette, and also when the smoker takes a drag or a puff. Right. And this was also tested in both in lab and in free living settings to be able to actually detect the smoking event. Another problem we tackle quite often in my lab, in the habits lab, is that of eating, right? And many of us know obesity is a huge problem, right, caused by overeating relative to need. We also know it's preventable, and it exacts staggering healthcare costs. So now the challenge with obesity is, unlike smoking, our treatment goal can't be to tell people to quit eating, right? Because we need it to sustain life. And so, however, as a computer scientist and as engineers, our approach is to use wearable sensing to detect and characterize eating episodes of excess calorie intake. And this is in hopes that we may detect it and design interventions that ultimately prevent problematic eating behaviors or overeating. So my journey here in the eating detection space started by using a piezoelectric vibration sensor. And here we're capturing the piezoelectric effect, right? And that's really the ability of certain materials, right, to generate an electric charge in response to force or mechanical stress. And so as we swallow, we generate these vibrations that we can actually begin to analyze, right? And so here we transform the signal in using a spectrogram, and we can see the frequency of the vibration surrounding the swallow. That center here in red around the middle of the time point centered around the swallow, we can see there's a clear difference between drinking water and eating chips. Fast forward, we moved we learned a lot from that. And so we moved to a non-contact sensing approach, where we use a proximity sensor, ambient light sensors, and motion sensors to capture chewing, feeding gestures, and also when participants lean forward to eat and when they lean backward to drink. So here, this is a video of a student that's actually drinking here. And here, as they're drinking, they're leaning back. We can see in real time the signal, right, and the lean back angle, right? And as they lean forward again, we can see the lean forward angle. After analyzing the lean forward angle, there are also chews and proximity signals. The proximity signal allows us to capture peaks also surrounding the chewing event, and the ambient light allows us to capture feeding gestures when there's a dip, right? So when a person has a feeding gesture that approaches, their hand approaches the mouth, we can see sort of the light the ambient light dip. Another wearable, again, we began to sort of advance our wearable sensors to incorporate RGB and thermal sensing. And here, the other sensing modalities did not always produce reliable results, and we always needed them to wear a second device to visually confirm the behavior. So we decided to merge the camera, the wearable camera that was used to visually confirm the activity in the field into our necklace. And here we used a thermal sensing array as well as an RGB camera to detect eating events. Here we clearly see someone eating rice and meat while socializing with someone else. And here to the left, to the right, you see the RGB signal, the wearable video, and to the left, you can see the thermal sensor, right? So we can capture not only when the hand approaches the face, we can get the heat signature from the head as well. And we can actually tell whether the object in hand is hot, the temperature, whether it's hot or cold. And so let's start, okay, here with step one. When we're talking about measurement, when considering the measurement device, we need to make sure that they understand the limitations of the device with regards to sensor positioning. We must understand its limitations. So when we were looking at the piezoelectric device that would touch the skin, in one of our papers, we also noticed a big difference in accuracy based on location, right, and positioning of this device. And this is going to be critical when training, people to actually wear or dom the device. We need to know the effects, right, on the signal as we move the device on the body. In another study, our goal was to capture authentic behavior. And so we looked at where to place the wearable camera to obtain greatest visual confirmation, right? So here, people were wearing a wearable wrist-worn device, and we wanted to know what was causing these false positives and false negatives, right, in the real world. And so we looked at where to place the wearable camera. We looked at the shoulder, the wrist, as well as chest locations. And in one experiment here, we see that the shoulder outperformed the others consistently when it came to detecting eating behaviors of interest, chews, swallows, feeding gestures. And again, depending on the activity of interest, the position will impact, right, the utility of the device. Another thing that's really important when it comes, and you guys are going to get a talk dedicated to human-computer interaction and user-centered design. However, I wanted to incorporate, something that I use quite often when it comes to optimizing some of the wearable devices that we develop or use. And sometimes when, the device that you have at hand isn't quite ready yet, right, or feasible, or acceptable when it comes to deploying it in the real world. And so I use this sort of iterative user-centered design approach to try to refine, right, this device. And so here you can see we run focus groups initially to understand context of use. We translate we specify the user requirements. We then design the system, whether it's an app or sensor or dashboard, and we have version X, right? And then we evaluate in a feasibility study for a given period of time. Could be 7 days, could be a week, that depends also on the sensor and the funding as well. There's a post-study assessment, and then we iterate, right? We look at whether we have sort of an adherence or feasibility measure that then allows us to know whether we need to iterate further, right? And so here, one big question often, and I use this quite often in NIH applications as well when I'm building devices and in training grants and planning grants. Here, we're looking also, we need to convince people regarding the measure, right? And also whether 90% is actually something that is achievable, right? And so there always needs to be these contingency plans. A great resource that I use quite often when it comes to acceptability, some of you might know this, comes from UW, is the user burden scale. And what I like a lot about this scale is it splits it into different domains, asks questions related to difficulty of use, the physical discomfort or comfort of the device, how much time is spent using the device, mental and emotional factors, as well as privacy and financial factors. Now, not all these components may actually apply. However, so for example, if in your study you don't actually include cost of the wearable device, you might actually take out that subscale. By the way, I'm curious, how many of you have used the scale before in your studies? Ravi, from UW, so you know this quite well. All right. Anyone else? Okay, great. Yeah, so this has been, I've used this quite successfully in several applications and in practice, and I've found it to be quite useful. All right. Another important thing that I like to highlight to a lot of researchers is to engage stakeholders early, right? Many times computer scientists engage, especially engineers, when we're developing these devices, we engage stakeholders late in the game. And this is a problem because we can't really understand their acceptability. So we might be developing a system or a device that people have no interest in using. And so in one example here, we showed clinical dietitians and tobacco treatment specialists our wearable camera. And we specifically asked them regarding their interest in using our wearable device in practice. This was an iterative, we performed 3 iterations of focus groups to learn about their acceptability. And there's a lot of qualitative data as well in this. However, here we show a lot of them were extremely interested or very interested in using this device, both the clinical dietitians and the tobacco treatment specialists, to be able to gain better understanding of eating and smoking behavior. All right, so addressing, now with all these studies that you're performing, some issues are going to arise. And one example of an issue that came up for us is, not surprisingly, the bystander problem, right? I mean, you have a camera. A lot of people have concerns about wearing wearable cameras, right? And so we studied different sensors that can aid in detecting the foreground and obfuscating the background. And so we thought, all right, what we really cared about was capturing the what's in the hand to know what the activity, the activity of the wearer, and we wanted to know. Sometimes we cared about the background, sometimes we didn't, right? But we wanted to make sure we couldn't identify people, and so we tested different obfuscation methods, right? And so we designed this wearable RGB and thermal camera. And the thermal camera helps us capture the heat of the hand and face. And so then what we can do is, make sure that the objects around the hand and the face are visible and objects in the background are blurred. And we tested different obfuscation methods, things like masking, a full-on mask right here that just shows us the hand and what's in the hand. We ran sort of canny edge detectors and things that allow us to just outline the object in the scene, but not show sort of the details of it. And then we had different intensities of that, right? Same with blur, right? We had ways of blurring the background and running different intensity blurs in the background. And in a study, we had many findings in this paper. One interesting finding is we showed about 379 Amazon Mechanical Turk users could detect the hand-to-head activity just as good as the as-is case. And we ran sort of a non-inferiority test to show that it was non-inferior in terms of detecting whether the person was drinking, eating, calling, or wearing glasses. So things that had to do with objects in the hand, when you actually had an object in your hand. However, with no hand-to-head activities, it significantly reduced the ability to detect the non-wearer's activity, particularly the ones with low intensity. And so here, we were looking at the bystanders and seeing, in some cases, they were in the toilet, in the bathroom, they were smoking, they were crying, drinking, they were sick. We had actors performing all sorts of scenes in the background. And then here we can see that when it's low intensity, with our obfuscation method, right, the blur, edge, all the other ones, they were not able to tell the activity type. Whereas in the as-is case, in the true raw video, you can actually see what the activity, they were able to detect the activity of the bystander. In the high intensity, where they were not, where they were moving a lot in the background, let's say they were exercising or fighting or praying, here we were able to tell their activity. So again, this was being able to tell the activity of the bystander, but not necessarily the activity of the bystander, but not necessarily the IDing the bystander. All right. So everyone here, engaging you a little bit, can you tell what this person is eating? This is an obfuscation method as well as the thermal sensor and us applying this obfuscation filter. You can type in the chat or raise your hand, blurt it out. Can you tell what this person's doing? All right, we got some things in the chat. Chicken wing, ribs. All right, again, another chicken wing. All right, let's take a look again. Whoever said chicken wing, you got it. That's exactly what it was, right? And so again, here you can see this was sort of what we started to show the users and asking them to tell us whether they can see what they're actually consuming or eating. We started to have fun with this, my students and I, and we thought, all right, can we start to cartoonize, right, the background, right, and seeing if this will actually increase their willingness to wear the wearable camera, and especially if we can personalize their own avatar and the avatar of the bystander. And interestingly enough, with certain obfuscation techniques, we can still tell that there is a screen, we can still tell that there is a bystander, but we can't really distinguish or ID, right, that bystander or what's going on in the screen. And so this helped us still gave us some contextual information surrounding the activity without sort of while still addressing the privacy aspect. So this gets me to my R01 that I'm running right now, where we're now testing in a crossover trial here, whether experimental trial to see if obfuscation has an effect on wear time. And here we're getting each person to try wearing the wearable camera with washout periods in between. And seeing and showing them their video at the end of the day or snippets of their video to get them to see whether that actually influences their wear time or not. So, so going back here, again, this changed, right? Now we started to think about wear time as more of an objective measure of acceptability, right? It's one thing to ask people if they're willing to wear a device. It's completely another thing to give them the device and see how much, whether they actually wear it or not. All right, so here's step 2, prototyping. Now in verification, we want to make sure that the device is still built correctly. Right. And there are many decisions that need to be carried out by engineers when deciding on what components make up the wearable device / system. And we published this as a guide for folks in a workshop at CHI this year, based on our experience designing this privacy conscious wearable camera. And it talks about different decisions that one needs to make, right, when designing hardware, ranging from sensor selection to how one selects a development board, whether there's a real-time clock on the device that continues running even if the battery runs out. All these things are factors that one needs to think about. And also whether someone should custom design their own PCB or use commercial off-the-shelf devices. We learned a lot from the fact that we custom designed our own custom PCB for our wearable camera, the initial version. It's really nice when you custom design because, it miniaturizes, makes it compact, really sort of efficient. However, we realized when we wanted to make changes to the device, it was a lot harder, right? And so this is where, we went back actually to starting to use some of the existing development boards out there, which are becoming really, really compact now with time and quite capable from a performance perspective as well. Another factor to think about when designing wearables and looking at the data is this notion of reliability of the sampling frequency. And so if you're told, or if you're expecting that the device captures 5 or 10 samples a second, you want to make sure you test that out, right? And so this here shows us a heat map of the data that we collected in 24 hours. And we see here that data from hours 0 to 3, data from hours 0 to 3 were good, and 10 to 19, but something happened, right, between hours 3 and 10. And we realized that another application on the device was blocking our application during that time. So ensuring reliability is a really, really important aspect when it comes to verifying the device. All right, here, another aspect that is really important is in verification is making sure the case design is polished. This is really important. It's sort of a catch-22 with a lot of computer scientists and engineers, because we're sort of, we don't want to go all the way when it comes to polishing and the device, but at the same time, we were testing acceptability, right? So that significantly, we know the look and feel impacts the acceptability of the device. So one thing we looked at here, was changing how we can orient the camera, right? Because everyone, depending on body shape, you're going to need to adjust the orientation of the camera to be able to orient it towards the mouth, right? Because we want to capture what goes into the mouth. And so we tested putting a hinge in different places. And we then added sort of cylindrical units. In the end, we added a half cylindrical housing for the camera that made it much more stable and was sufficient for the range of orientations we wanted to capture. Another factor that always came up when it came to deployment of our wearable devices was considering what might happen if someone was to drop the device, right? So we did these drop tests, right? If someone was to actually drop it from 6 feet, what will happen to the device and system? Can it absorb the shock or not? And is sort of the 3D printed case drop safe or not? So now moving towards the last step that we'll cover in the talk is that of validation. And here we're asking again, one of the most important questions is the biomarker that we're generating meaningful? And, while this may seem obvious to a lot of folks, many computer scientists, engineers may build a system that's not really tested in the population of interest. And many times it is a convenient sample of students. It could be primarily due to funding and time constraints. or even lack of motivation, maybe the motivation that we found in Jane Goodall, for example. But in a recent model and a recent publication, we show that even when you train an ML model on people without obesity, it shows, and here we trained a model on this wearable necklace to be able to detect eating activities. It shows poor performance on people with obesity. Again, thinking about what may bias our digital marker is important, right? And how we actually translate, right, those signals into meaningful biomarkers, right? And how our ML model was trained is essential. All right, determining our ground truth measure. Because we do a lot in the eating space when detecting food intake, many often resort to using food logs, right? Using smartphones. And when funding is available, we often use sort of 24-hour diet recalls, which is still considered a traditional standard in dietary assessment. However, we also wanted to know, and we believe it was essential to visually confirm when visually confirm when there were false positives and false negatives out in the field. So we also augmented using a wearable camera. And this is primarily, right, this ground truth selection is primarily when, necessary when it comes to activities that you can visually confirm. Now, as you know, and Jim covered as well, when building these machine learning models, it's going to be important, right, to consider annotation and labeling. And so first, we want to start with our hypothesis, right? What features matter the most? And so in one project, we were looking at a wearable wrist-worn device, and we wanted to see whether we can actually detect swallows, bites, and feeding gestures. And so the first thing we need to consider when labeling this data is, how are we going to confirm the activity of interest, right, or label it? What's our validation method? And so we need to make sure that the camera can, if we're using camera, can actually capture the features of interest. And then we need to develop a labeling scheme. Then there's data collection, and then we label, right, using software. And this is really important. We actually in the lab have sort of not, trained labelers and also novice labelers. This is extremely takes a lot of time, right, to label and annotate data. And so it's really important that a proper mechanism is set in place for annotation and labeling. There are many companies now in place actually that can help as well with annotations, although we still need trained labelers and a proper schema to double check their work. So let's start with validity of camera. Here, let's see. All right. So here we're testing smoking, and this is actually part of the MD2K project when the participants actually smoking in a lab setting. And so a stationary camera is sufficient for us to be able to capture the activity of interest. Here we see a feeding gesture happening out in the wild, right? So in eating episodes actually occurring out in the field, we're going to need a wearable camera to be able to validate or label or visually confirm that activity. So here we can see a person eating, and there's actually another person next to them also eating. And here it's actually the wearer is wearing the shoulder camera. And so the first thing we need is our labeling scheme. And this is also a challenge, right? Because it may seem very trivial, right? A feeding gesture is a feeding gesture. What's so challenging about that? But there's so many nuances, right? Is it a duration in time that you care to label, or is it a single point in time? Is it a bite or an entire gesture? Is it, a gesture from the dominant hand or the non-dominant hand? Is it a feeding gesture from both hands, right? So all these things need to be considered when labeling. In the MD2K project, this was, we collected data having proper data collection protocols is really important. And here, oh, that was, I guess Siri thought I was talking to it. Here, we see the MD2K team where they come in for an initial in-person visit and perform different activities and confounding activities with the wearable wrist-worn device and their sensing suite. And they wear the camera and devices from day 2 to 4. And then from day 5 to 4, it's the post-quit phase. And so here we're just looking at the time when they're actually wearing the wearable camera. And so here, this is us using Elon, right? We first load our video data from the camera data. We then need to we then now start labeling, right? And so here you can, what's nice is you can actually zoom in and zoom out. And then we need to find, right, that time point where the person is actually smoking, right? So here we start watching the video and then we see when they're about to take a drag or a puff. We pause the video, rewind a bit, right, to adjust, right? And then we actually select, right, the duration and time from the rest, from rest all the way to when they take a drag or puff all the way back to rest, right? So that's how we define an actual smoking gesture, from when they pick up their hand all the way to when they go back to resting their hand. And then we label it as SD, smoking with the dominant hand. And then here you can actually, what's nice about Elon is it allows you to spit out the start time, end time, as well as duration of these labels into a file that can be then used. So here, another issue that we have when it comes to annotation and labeling, you can label the video data, but when you have to synchronize the data with the wrist horn sensor, there can be challenges, right? Because there can be an offset, right? Many devices run on different clocks and their clocks drift apart. And so one needs to make sure to align them, especially when we care about fine-grained behavior that have tight bounds on time. So here, again, we calculate the relative time of the wrist data, we load the video and signal file, calculate offset, we edit the offset, confirm synchronization, and then we iterate. So before, you might have the relative time as 9,000 milliseconds, but there might be a 9-second offset. We would just set that adjustment in Elon. Here's a nice video that shows us how to do this. Here we have 4 dominant drinking DD gestures with the dominant hand. And we can see, labeled from the video data, we can see here that there's an offset, right? There's 4, and here are the 4 drinking episodes with, this is the wrist one, accelerometer data here. And so what we do, as you can see, what we do initially, the labeler will then start by looking at the offset between one of these times, right? So one of these, the offset right here, all the way to the beginning, right, the end of this dominant drinking label. And we can see here that it actually says about 9,000 milliseconds is the offset. And so we can actually open up Elon and enter an offset in time here to say that the time between the wrist-worn device and the video, there's an offset of 9 seconds. We make this correction. We can see here they're all perfectly now aligned together. This is going to be really important prior to training our machine learning models to make sure that time is aligned and is synchronized. After labeling an eating episode, you then have this file that's generated with big, start and end times, as well as duration times and the labels of whether they were from the dominant hand or non-dominant hand, and whether it's feeding or drinking gestures. So this spawned, again, this is cumbersome and burdensome, right? To be able to spot, right, these activities to synchronize across devices. And so this spawned an area of research and actually collaboration between Santosh, myself, Jim Ray, and Bonnie, quite a few of the folks on the call today that you learned from today kind of unites us all, this ThinkWise paper. And what was nice about this is we're actually taking signal streams from an accelerometer and a signal stream from a wearable camera and looking at the motion in the accelerometer stream and motion in the video camera or features in the video camera and trying to auto-align them. So think about feeding these two sensing streams into the ThinkWise algorithm that we designed, and the ThinkWise algorithm will automatically tell you this offset. This has been an interesting area of research as well, working on time syncing between different devices. Another area of research that this actually spawned is looking at active learning and the potential of active learning. Do we really need all these labels, right? Can we learn and build machine learning models with just a subset or a fraction of the data that we're actually collecting? And so here, from our NextSense paper, we actually published another paper that looked at using active learning to be able to determine, right? So here you see an easy to learn in the red proximity signal, right? These are chews, distances from the proximity sensor on the neck to the chin. We can see a clear, nice chewing signal. This on the left is also a chewing signal, but it's a hard to learn one. Perhaps the person was wearing the device incorrectly, or perhaps we were just getting, a poor signal. There are different now active learning techniques that allow us to identify which parts of the signal we need to label, and then giving that to the annotators and labelers to label. And that way we can, instead of labeling all the data, label a fraction of it and still be able to obtain a good enough model or as good a model as in some cases we can get from labeling the entire data set. So here we show, using this cluster maximum entropy plus AMU algorithm that we proposed, that with a fraction of the data, we're able to reach accuracy, the same accuracy as we were able to get with data trained on 85, or a model trained on 85% of the data. And so by looking at training a model using less than 1% of the data. All right. So just to summarize, we looked here at, are we building using the right system, right? Looking at measurement, sensor positioning, iterative user-centered design, engaging stakeholders early, feasibility, acceptability measures. Was the device/system built right? So looking at different prototyping platforms, reliability, case design, and also looking at validation, right? Is the biomarker generated meaningful? And looking at making sure we tested on our target population, being careful with the ground truth measure we use, different annotation and labeling challenges that might arise along with time synchronization. And so I wanted to end my talk by looking by this nice quote by Jane Goodall. And every time, she says in her latest movie, Jane, every time I would try to get close to the chimpanzees, they would run away. I was worried the funding would run out before I would find something really exciting. I was going to try to get the chimpanzees used to me so that I could really learn about what they were doing. And the only way to learn about them is when they know you're there, but they ignore you. And I know I presented a lot of challenges, but these challenges also turned into opportunities and new findings. And like Jane Goodall said, it's challenging, in a similar way, it's challenging to use these devices and these systems, but the potential to finding something really exciting is great. So again, please don't be afraid to jump right in. And with this, I take questions.
Perfect. Thank you, Nabil. So, scholars, any questions?
I have actually overview type question is as first of all, great presentation. And I really like the part where you talked about when you're thinking about designing sensors or which system to use, thinking about from the table, like what are things we need to do, right? So when we are doing this or you are planning that, how do you envision or like user adoption in the longer term? And thinking about privacy and other concerns, because a lot of times in digital health studies, we have seen this issue with like trust from different demographic groups, that they don't trust us, and we have to build like communities, and it takes a lot of longer time. So how you like put that into perspective when you're thinking about which sensor you are going for to build such a system, like a multimodal system?
That's a really great question. It was so challenging for me because here we were building all these wearable devices, to capture eating, and then when we would go out into the real world, we didn't really have a good way of visually confirming the behavior. And then we started saying, all right, let's use this wearable video camera to visually confirm the behavior. And then after a while, we started saying, okay, let's make this this video camera, this sensor, right? Let's take this, way of validating and make it the sensor. It was challenging, right? Because again, of this privacy concern. And, this is really, what it comes down to is user-centered design. This actually was a culmination of many, many years of work, all the way from our I Can't Be Myself paper back in 2018, to what we have right now, right? Trying to see that, there are different things that people care about, right? The device affordances. It's not just what you collect, right? So some people, for a lot of people, it was the device orientation, right? The lens. Them simply seeing the lens was a concern to them, right? And, when we oriented the device, as opposed to the egocentric view, which was looking all the way away from the wearer, when we oriented it towards the mouth, it was a lot more acceptable. For some people, the device affordance of having the camera on the wrist was wonderful, right? I could sort of hide it when I need to. And, when I'm eating, it shows up, right? And still captures what's in my hand. So again, it's really disorienting for the annotation and labelers to see the video from the wrist-worn device, because you can imagine what our hand does. Generates crazy, unstable video, but really a lot of user-centered design, right? And engaging stakeholders, engaging the users, and we still are to this day. So right now we are looking at integrating this with clinical dietitians, and now we're sort of in that, looking at that implementation phase and starting to see what might be other challenges, that might come our way. I hope that helped answer your question or part of it.
Yeah, thank you.
Nabil, let me ask you a question. So many of our scholars are clinical implementers. So this may not be a alternative they have to devise their own device. So they may end up using off-the-shelf devices like Fitbit. What are some of the high-level challenges they would encounter when it comes to extracting digital biomarkers from those commercial devices, sampling size,
Yeah,
and
yeah. No, great question, Vivek. From the commercial off the shelf, again, because of the challenges of dealing with companies, we always resort to building our own systems. But again, they've tackled the look and feel and all these other challenges they've already addressed. And so Fitbit and a lot of other companies now have the ability to extract a lot of meaningful information and data, and even raw data. So actigraphy as well has the ability to extract some of the raw data. Again, it all comes down to what is it that you want to validate, right? Physical activity has been an area where a lot of people have tackled, right? And so, the accelerometer and gyro gives us good information as to the intensity of the activity. But when it comes to other behaviors like eating, like smoking, etc., I do recommend a phase or part of your study incorporate the video camera, so that you can know when your device fails, right? And when it succeeds. And this is going to be important. For example, we realized in one study that, every time, our device would get a lot of false positives every time someone would use their smartphone, right? Or would go on a phone call. There'd be a lot of wrist motion there. And so if we simply integrate data with the smartphone, we can tell, right? We can be able to infer, right, or know that this is potentially a false positive. They're not actually eating, they're just using their smartphone. So knowing when your machine learned model fails is going to be critical. And so that's why, sometimes reviewers will come back at you and say, well, are they going to wear all these devices, right? And, that's why you have a portion of it, right, where you're validating a portion of your study or part of your study where you're focused on validating that device that you're using. They don't need to be wearing the wearable camera later on, right? That's just a refinement phase, right? I hope that answers your question, Vivek, or part of it. There are many other challenges again with companies like cost, etc. But yeah.
Scholars, any other questions?
Nabil, thank you so much for a great talk. I was just wondering, kind of spinning off of some of these questions that we had already, but just thinking about seeing as, you're really developing new hardware and software. So I was just wondering, would there be sort of a translational pipeline of your dream, maybe sort of a company coming and picking up sort of the hardware and producing it at scale, or what would sort of be the dream for you as a scientist in this space?
Yeah, you spoke my mind, Olga. Yeah, so we're in the midst of we started a company actually called SenseY Incorporated to answer sort of the question of why use a particular sensor or not. But I do think that relationship with industry is going to be a critical one when we're thinking about scaling, right? We have too many systems right now that are built, right, designed, and then once the funding goes, that's it. The system no longer functions. And so this has been a critical, area of inquiry, something that we need to think about as a community, how we can sustain these systems that we're building, right? How we can begin not only engaging the stakeholders and the participants, but actually engaging the research community. And so I think that my dream would be that we have these companies that allow us that stick with us, right? And always provide sort of support at a cost, but provide that support. Unfortunately, one other thing is when people get FDA or companies get FDA approval, another challenge is cost goes high. skyrockets up. So that again poses a big challenge for researchers, right? Thanks, Olga.
Perfect. Let's take one more question so we can end on time. Any other questions?
I had a brief question about length of time. So, and I know you mentioned that you were looking at possibly partnering with dietitians and who would potentially work with patients over time. Of course, we work with patients over time, and I can see this being very valuable. Then I started thinking about participant burden, like so, because I saw like 3-day window is different than asking someone to maybe wear this and maybe, have this information or be willing to provide this information over a length of time. So how is that something that you'll look at or have looked at, and can you share what you found out?
Yeah, no, great question. And again, in a lot of our studies, we pay our participants, right? And so what happens when you take away that payment? So great question. Right now, we are looking at this more with the clinical dietitian more as a diagnostic tool that can aid in sort of allowing us to understand, the contextual factors that surround the problematic eating behaviors. They rely a lot on self-report measures, and we know, I shadowed clinical dietitians and Bob Kushner, for example, at the Lifestyle Medicine Center here at Northwestern, and you see sort of a lot of time is spent on recall. What did you do the last month or two, or the last week or yesterday? And if we can streamline that, if we can auto-detect these videos and watch the video with the participant and begin to sort of really hone in on some of the contextual factors that are influencing their problematic eating behavior, then perhaps we can really design a treatment that's personalized to that individual. So right now we're looking at it more as a diagnostic tool, but we'll see where this goes.